Hi, good morning, everyone. This is Ali Rasek. I'm a structural engineer with HDR, and today I'm teaching Civil 459 Earthquake Engineering on June 14, 2024. And let's see if we have a good momentum here. 15 people, not bad. We will get to over 20 in a few minutes. Yeah, just tell me if you are not hearing me. Yeah, again, some new microphone here because I'm at work. So I have changed the microphone quite a few times. So hopefully this is working again. And we should be good to proceed. Yeah, so we are halfway through module number 5 now about earthquakes. Generally, high-level information about earthquakes that any earthquake engineer should know about. And it's beneficial in understanding the information you receive from geologists and geotechnical engineers. About next week, we will proceed to a National Building Code of Canada, which is probably, I can call it the most important part of our course. But I mean, it depends. For everyone, the most important part is different. But for a lot of us structural engineers and for people who like to have a career in building engineering, NBCC is top of the list. We will focus on section 41A, which is mostly about earthquakes, earthquake loading. And yep, people are still joining us, which is okay. And yeah, what I was trying to convey is that, yeah, so we will focus on National Building Code 2020. I think I browsed through the internet and I saw that it's now legislated in BC. I don't know why, I'm not sure why 4 years too late, but this is legislated in BC, so we can really confidently focus on National Building Code 2020 rather than 2015, which was previously the law and legislation in British Columbia. However, if you guys have, for some reason, you have a preference for NBCC 2015, let me know. And if some of you have preference for that, I may try to parallel because there have been some substantiated change in the way they look at it. I think it's the same results, but slightly different way of looking at the procedure for NBCC in 2020, which is now the legislated in BC, and we can focus on that. So today we are at about 14. Yeah, so we are progressing well. We are trying to finish module number 5 today, and yeah, that which means that we are on time. And as I said, because we have fewer presentations than I expected, we even have about half a session here to even do more if you have anything. Or I'm also trying to find a guest lecturer, especially in the area of wood design and earthquake design for wood. Yeah, that's not my, I can't consider it my top expertise. So I'd like to hear from somebody with more experience than me, but I haven't been lucky yet. Everybody is busy or traveling, etc. However, that's what I'm thinking, that for this half a session we have on wood, or have a module, one session that we have on wood. If I find a industry expert on wood design, then I will invite them. Other than that, hopefully you are progressing well with report. Email me if I can be of any help. And in a couple of weeks, I expect to receive the draft report. And let's go to the presentation. Last week, we progressed as far as we went through seismology. I think, yeah, right here. So if we can remove this. Yeah, we were talking about different types of waves that are important to earthquake engineer. And as I said, the top two ones are the most important ones that we discuss a lot when we want to talk about wave effect on the structures. Basically, the waves that travel through the body of rock from the hypocenter to the location of our structure. One of them is mostly axial, and we call it pressure wave or primary wave. And the other one is secondary wave or shear wave, that any node, any point on the shear wave, it moves perpendicular to the direction of propagation. So the wave is propagating in this direction. However, the vibrations are perpendicular to that direction. That's the characteristic of the shear wave. And for primary wave or pressure wave, okay, maybe you made it inside the class. Basically, yeah, so for pressure wave, the vibration is at the same direction as propagation. Then we have the two important surface waves. One is called the love wave, and the other one is called the Rayleigh wave. So the importance is at the surface. When the wave hits the surface and then propagates on the surface, love wave propagation is like parallel to the surface of the ground, and the Rayleigh wave propagation is perpendicular to the surface of the ground in a way, creates hills in a way, or pseudo hills, temporary hills, but love wave is more like to the right and left. Then we saw this picture from Christchurch 2011, where the love wave has caused this right and left basically deformation because of the wave that went through this point. Now, how can we, like normally, like after an earthquake, we receive reports about epicenter of the earthquake, and I already showed you the diagrams from accelerograms in Turkey, but the location of the epicenter or the distance to epicenter was noted. And how do they do that? They need at least 3 stations. So, I mean, nowadays there are plenty of stations almost at any place, any earthquake zone on the planet. So there are enough recording done, but at least 3 of them are required to get the location of the epicenter. And if we have more, and we have more, it will increase the accuracy. The arrival times and velocities of P and S waves are calculated. So basically, for each epicenter, you calculate this radius, like how far the epicenter is. For B, it has determined to be 5,600 kilometers, a circle is drawn. For C, it's determined to be 8,600, another circle. And for A, it was determined to be 1,500 kilometers, a third circle is drawn here. Now, the point that all these three circles meet is the epicenter. And like how we calculate the radius for each of these circles is basically based on the speed difference. So a speed difference and arrival difference of the two waves, the P wave and the shear wave. So the shear wave velocity is known at the rock, and the P wave velocity is known at the rock, and basically the accelerometer here or the sensors here, they can determine the arrival times for each one. So we are focusing on B. The arrival time for shear was TS. The arrival time for axial or pressure was TP. And we know the velocities, so we can use this equation and find the radius at point B. We have similarly for station A and station C, we calculate the radius to epicenter, and where these three circles meet each other is the epicenter. So that was like maybe a question of interest, that how we know where the epicenter is. We refresh you one more time on epicenter. So epicenter is the point on the surface right above the hypocenter. Hypocenter is exactly the location that the earthquake energy is released at breakpoint in a way on the fault, where it couldn't hold, they couldn't hold to each other anymore, the two sides, and the break happens. So a lot of energy is released at hypocenter, and epicenter is the point right above it. And yeah, I showed you a solution where we can calculate the location of epicenter. Now the next topic on intensity. So yeah, throughout the history, engineers, or the modern history, where the engineering has become important and saving life has become more important. It has not been forever, but recently in the past century, good engineering and saving lives has become more and more important as a phenomenon, a modern phenomenon. It has not been there through the history. Basically, so engineers, or engineers generally, they were interested to know how intense the earthquakes are at each zone so that they decide accordingly. One of the earliest measures of intensity is called the Mercalli intensity scale, and that's a scale of intensity and strength of earthquake. Mercalli innovated that, or created that scale factor in 1902. The issue is that it's slightly subjective, so it's mostly based on observation, and observing the damage gives us the intensity scale. Right now, the current value of it is for historic analysis, and it varies with the central distance and construction quality. So it's affected by these two factors. And so for a certain region, when you want to determine the Mercalli intensity scale, say for intensity 1 to 3 is what was not really felt, and except if there is some special circumstances. And 4 is generally felt but not causing damage. And 5 is felt by nearly everyone. So if almost everyone with any attention span or sensitivity realize it, we are already at 5. I said that it's subjective, so it's a lot discussing about how people understand it quick. 6, level 6, intensity level 6 is some heavy furniture is moving and maybe some plasters are falling and chimneys are damaging. Level 7 is negligible damage in well-designed and constructed buildings. So even the good buildings will start to have some damages at level 7. Level 8, depending on the quality of design and construction, damage ranges from a slight to potential collapse. Chimneys, monuments, and walls fall. So level 8 is really intense in this scale. The top intensity, really damaging earthquake. And if a building is not designed well, the damage might be substantial and it could be near fall. After level 8, starting from level 9, even the well-designed structures could be really damaged and permanently wrecked, partial collapses and building shifted off their foundations. Level 10, some well-built wooden structures destroyed, along with most masonry and frame structures. Level 11, few, if any, masonry structures remain standing. And level 12, most construction severely damaged or destroyed. So that's the largest intensity that they could imagine. Modified Mercalli intensity scale, distribution of modified Mercalli intensity for 1989 Loma Prieta, California earthquake. That's a modern earthquake shown in Mercalli scale. So as you see, it's distance related and based on general observations. So it ranges between 8 and 6 in this region. So this region is mostly 6, 7, and 8 when you get very close to the fault location, close to Santa Cruz. And here is Palo Alto, so San Francisco is up there. Earthquake magnitude. Earthquake magnitude measurement is quantitative. So that previous one was intensity. This one is called magnitude, which is a more modern notion. It's quantitative, so we try to not be very subjective. So based on what we observe from seismographs, single value correlates with energy, and we try to, like, energy is a good measurement for earthquake, how much energy is released, and therefore we try to correlate it with energy. Logarithmic scale is used, meaning that when you go 1 magnitude higher, the energy is 10 times. Sorry, the amplitude, acceleration amplitude is 10 times, which means the energy is about times larger. So it's logarithmic for amplitude of displacement or acceleration. And the variations that are like different people who have researched this. Richter used to be the most popular one. Body, surface are also important, and moment is the latest and greatest. So now most of the discussion is about moment magnitude, but Richter used to be more popular. Now, what we expect to see, we want to have almost same scale as intensity that we previously discussed, but they cannot align really exactly, but we try to have almost the same numbers as intensity. So say 2.5 or less, usually not felt. It was almost similar. We want number 4, like between 2.5 to 5.4 to be felt epical with minor damage. Between 5.5 to 6, some damage to buildings. 6 to 7 may cause major damage in populated areas. Then going 7 to 8, causing serious damages. And greater than 8, great earthquake that can totally destroy communities near its epicenter. So that's basically the mindset that we can have in mind. The important numbers are normally greater than 6 that cause major damage up to wiping out communities. Earthquake magnitude scale. Richter magnitude was developed by Charles Richter in 1935, and basically based on it's called ML, and ML is basically the ratio of amplitude to a calibrated, like the amplitude calibrated to an A0 value, and then the logarithm of it. We said that it's logarithmic for amplitude. Therefore, each time the amplitude, the ML increases by 1, means that the amplitude has raised by 10. Goal was to quantify medium-sized earthquakes between 3 to 7 in Southern California. Limitations, ML around 7 for all large earthquakes. Unreliable for measurements more than 370 months. For MW more than 5, we have better used the moment magnitude, which is what we see in the books and reports right now. Moment magnitude is the latest and greatest on basically calculating the magnitude. And it's based on the rigidity of rock multiplied by the slip that happens between the two sides of the rock. And MW is called MW notation, use MW notation here, is calculated by this equation based on moment. That's why we call it moment magnitude. And like say for 1960s Chile earthquake, it was 9.5. And for Alaska earthquake in 1964, it was MW 9.2. So it's useful, or we are told that it's useful for larger earthquakes or greater earthquakes. Moment magnitude is definitely the one to use for reporting. And as we said, the magnitude greater than 5 is what we really care about. Basically, a comparison between different scales. This is ML by Richter. We said that it's like who originated these comparisons. And this is moment magnitude, which is like the latest in the series and the most important for us. And Richter, these two are by Richter or different variation of the Richter magnitude, which used to be the most important, but lately it's completely replaced by moment magnitude. Like if you want to use them, what size of earthquake? For a small earthquake, observation is good enough. For small, the moment magnitude, the Richter magnitude is important, which we said is based on amplitude. And for large earthquakes, very large earthquakes, the moment magnitude, or basically for all earthquakes at all depth and all epicenter distance. So moment magnitude, it calibrates well all every earthquake, while there are limitations in using the other ones. The reference parameter wave amplitude has been for Richter, and seismic moment has been for moment magnitude. Not sure why it says for Richter it's related maybe to wave amplitude, but it's mostly observation rather than measurement. And applicability, it's regional, mostly created for California, but others have been used worldwide. And saturation, I think it cannot be used for greater than some value. They have an upper limit, and the moment magnitude has no limit. So moment magnitude is what we really use right now in engineering. Earthquake energy release based on magnitude. So on the left, it's the magnitude going between 2 to 10. And we said there are different scales. Sometimes they match well, sometimes they don't match well. On the right-hand side, the energy release, like how many kilograms of TNT you need to create that energy. And you can see that it's really exponentially goes up when you change from magnitude 2 to 10, or even say for the felt earthquakes from magnitude 5 to magnitude 9, still exponentially up. But the number of the earthquakes that happen per year goes exponentially down. Like, say, for about 10, we only had one in Chile, but for magnitude 2, order of million happen every year. So magnitude 2 happens a lot. And it reduces really by magnitude, going down to only 1 per year for magnitude 9 or less. Some years we have magnitude 9, some years we don't have. Magnitude 10, apparently Chile was reported in 1960, and I'm not aware of more than that. So getting a sense of the energy release and how occurs, the number of times they happen. Astronomic motion instruments, how to measure astronomic motions. So digital astronomic motion instrument in RC Vault. So this is a digital astronomic motion instrument shown here, and insulated cover and solar panel here. So some of them use solar panel, obviously, because they remain in the wilderness for a long time, and they should keep on functioning until an earthquake happens with a strong ground motion, noticeable ground motion, and the recording are useful for us. What they produce is acceleration time history and velocity time history and displacement time history, which are important for our design. Basically, if you want to think simply about them, most of them are really mass and stiffness and damper system, and the response to the earthquake. And we know that we have equations for that response, and we can calibrate it so that they really note down the response in terms of acceleration or displacement. Most modern instruments are even more complicated, but that's the basic idea for a strong ground motion instrument, or sometimes we call it accelerometer. Yeah, so that's this slideshow. Tell me if there are questions. Otherwise, we move on to next one, continuing with earthquakes. Part 2 of earthquake, which is about site response and seismicity. Let's give it a few more seconds. Okay. One more chance for questions and comments. Let's proceed with site response. So in the previous slideshow, we talked a lot about the source of earthquake and the way the earthquake will come from a hypocenter to the surface and hit the ground at different locations. However, the site response is important, which is an emphasis on the layers close to the structure. So the layers close to the structure could be soil or liquid rock or a strong rock. And yeah, so for site response analysis is a lot of geotechnical, basically geotechnical engineers are in charge of creating the site response or discussing the site response for us, but we should know what they consider. So the first consideration is performance objective. Remember that we had a discussion about relation of performance versus the objective that we have in mind, like life safety versus collapse prevention versus damage control and versus operability. So we should know the performance objective, and based on the performance objective, we determine a return period for our earthquake. Say like typical numbers are like 500-year return, which is like practically for 475-year return, which is mostly for operability of dams, and for a lot of dams in BC, 10,000 year is for damage control. Hazard definition, number 2, outcrop motions, response spectrum, and records. So if you're a geologist or geotechnical engineer, they will provide outcrop motion. Right? What if you have competent rock at that location, what is at the competent rock location. You see that this profile is the competent rock, like a rock which is strong enough. And we want to know what is the earthquake at that location. So that's what the geologist side is more like geologist side. That's done by geotechnical engineers as well. The earthquake that could be felt at outcrop. Step number 3 is the site response. That is really done by geotechnical engineers. They take the outcrop and they develop it through the soil layers to get the earthquake that really is applied to your structure. So you should be aware of this process, and in a way NBCC also mimics that, provides modification factors that modifies the outcrop response to the site response. But for more detailed analysis and design, the geotechnical engineer would do that. So that was a step number 3, site response. We get the free field motions. And the free field motion is normally the outcrop, we call it free field motion. And the soil performance, which rock soil performance of different layers will affect the site response. Soil and structure interaction, which means how the soil, nearby soil, is interacting with your concrete foundation, and how this interaction will result in the movement of the structure. For that, you also get some help from the geotech side. And step 5 and step 6 is really the top responsibility of a structural engineer. What is the structural response? How the structure deforms, and what is the performance that is showing? We discussed the performances. And component response, which means how each member responds to the earthquake. So 5 and 6 are the top responsibility of the structural engineer in a way. However, because we are dependent on the previous steps, if the previous steps are wrong, then our design is wrong. So in a way, we are responsible for the previous steps as well. We should be very careful with what we receive from geologists and geotechnical engineers. Again, more on site response. And so these are the recordings, say, in terms of acceleration in time. So vertical coordinate is time, and it's showing the acceleration. So each one of these, like 3, 4, 5 recordings. Assume that you have accelerograms on different locations. The one that sits directly on the bedrock sees this acceleration. The one that is sitting on a stiff sediment, it's in this. Recording on the soft sediment depends on the depth of the soft sediment, and the softer the sediment becomes, you see wider displacements and amplitudes. So this is basically emphasizing the value of site response. And if the engineer naively uses the outcrop, which is on top of the rock, they are underestimating the response. While if the building is sitting right here, the response should be much greater. So the structural engineer is designing beams and columns, but they should be super careful what site response they are receiving. If they are given outcrop, they should object and say, no, my structure is on the soft sediment, and I really want the site response there, which could be very different. The importance of the site response, like it's important in all earthquakes, but it was really like it was shown during Mexico City earthquake in 1985. That's a classic example that is discussed in earthquake engineering courses. In 1985, an earthquake with magnitude 8.1 happened in Mexico City. And so it caused a lot of destruction, but most of the destruction was in mid-height buildings, like buildings about 20-story high. As you see, a taller building is sitting well, and regular houses were also sitting well. So one could blame the quality of work in mid-height buildings, but we will see that it was found that the site response was responsible for that issue. Again, more pictures of the mid-height buildings collapsing or being damaged. Now we come to the issue with the site response. And so the bedrock period between 0.95 seconds and 1.9 seconds, and leg bed period between 1.8 seconds and 2.1 seconds. So basically the city is built on sediments on top of a lake bed, and as you see, the periods on top of the sediment has changed a lot. So the input has become like 2 seconds, the period has increased, the acceleration period has increased. We can look at this more carefully. PGA at the bedrock was 0.04 G, so it was not like the largest PGA that you can imagine, much lower than that. That's the response spectrum at the bedrock. However, the response spectrum on top of the lake bed, like on top of the sediment, bottom of the lake, had increased by a lot. The biggest change was for periods of about 2 seconds, where the peak response acceleration at bedrock was 0.1 G. So say here, the peak response was 0.1 G. So this is the a spectral acceleration unit of G, and this is period unit of seconds. But so the largest value among the whole curve for bedrock was 0.1 G, and the largest response for the lake bed among the whole curve is a huge value of 0.9 G. That's where those 20-story buildings come in. Those 20-story buildings, they had a period close to 2 seconds. I mean, you will learn that more, and you will study that more. You can use the code to obtain period of structures, and you can see that for mid-height, 2 seconds is a typical value, plus minus. But then if you go even plus minus, you see that you are all still in very, very high response zone. Again, another picture comparing the PGA at exactly the epicenter location and PGA at the lake bed. Peak response acceleration at epicenter was at about 1 G, and peak response acceleration at lake bed, which was 0.9 G. Again, lake bed response was the most important one. The design, so the recorded value is this one, and the design value per the code that they were using was this one. While for epicenter, the code was recommending this spectra, while the recorded value is this. So for, say, for the epicenter, these two values are very comparable, so the design was fine. However, for the lake bed, which where the city is, and particularly for a period of about 2 seconds, the difference is substantiated. So basically, a good engineer was designing for this point, and practically what happened was this point. The site response was important, and it was not really considered. Yeah, another view of the site response issue. So how for sophisticated problems, how a good geotechnical engineer will perform site response analysis. They apply quiet absorbing boundaries at the base, and they apply the earthquake excitation at the base, and they measure the response at the location of the structure. Or a typical 1D solution is here, how the wave moves from one layer to the next until it hits the surface. Again, here, schematically, a bedrock is shown, and if you measure the response or calculate the response at this point, that's what you expect at the top of the competent rock. However, in case of Mexico City, a lot of buildings were sitting on a soil, and that's why the response was different than top of the bedrock. So they can use, you can use, or geotech engineer can use different software to go through this process and really calculate the expected response underneath a very important structure. For more regular structures, the code recommendations should be good enough. Again, more discussion of the site response and how basically a spring and damper models are used in different layers of soil by the geotechnical engineer until they give you the surface response. And then the structural engineer uses that surface response at the base of the structure they are designing, multi-story structure. And soil structure interaction is sometimes considered. Sometimes we model, like in the more advanced analysis, we model the soil and the structure simultaneously. So remember that this one was like a two-step solution divided between disciplines. So the geotechnical engineer is in charge of the left-hand side, and the structural engineer is in terms of the in charge of the right-hand side. And here is a mixed model of both. So the soil is considered in one model with the outcrop excitation, and a mixed model could be made that has both the soil and the structure, which the interaction between the two is also considered. And say in plan view, maybe you have competent rock all around, and the soil area is here where interaction happens. So issues to be aware of. Maybe you don't go to too much detail during this course. Now, yeah, so tell me if you have questions right now, or I mean, later on you can email me or call me with your questions. Okay, now going into the different types of the ground motion models that we receive from the seismologists or geotechnical engineer. Basically, maybe the top two rows are the most important. So different types of ground motion models. Some of them are a spectrum, so we may receive them, or they can develop for us in terms of a spectrum. Remember spectral accelerations that we discussed quite a few times, and or we receive them in terms of time histories. Like here, so this is like a spectrum, say a spectrum defined by the code, and a spectrum from real earthquakes. Either one of those could be provided by geotechnical engineers or geologists for our design, our building design using RSA, response spectrum analysis, versus records, real records or manufactured before manipulated records that geotechnical engineers provide for our design, structural design. So record versus time history record versus a spectrum. We receive one of the two. And for a spectrum, they are like code provided ones. We will see how NBCC asks us to create a spectrum, which is very important. We have a process for that. That's the most important thing, or one of the most important things you learn through NBCC, how to create the design spectrum. They could be based on record. So you have a record and you create the correlated spectrum. Site-specific, they come from site-specific studies, which are important. And power spectrum, I have not used, but so I have been familiar with this code created based on NBCC or American ASC 7 records. When you have a record, you can change it to a spectrum. And site-specific is what the geologists provide to us. And each one of them could be normal or artificial, depending on the case, or elastic or inelastic. Normally, we are more interested in the elastic ones. I mean, they appear to be elastic, but they are created to be used in elastic cases as well. Time histories, again, they can be recorded from the site, or they could be even artificially created. So that's the important issues on this slide. Probability of accidents, we already discussed that a few times, or we used that term a few times, but here is a more careful look at the probability of accidents. Return period of significant earthquakes tend to be very long. How likely is that event to happen in the lifetime of our structures? Say a lot of structures have 50 years. 50 years is a good number for a life of a structure. And if an earthquake is happening once every 2,500 years or 2475, what is the probability that it happens at least one time during the lifetime of the structure? The probability of at least one earthquake in 50 years is typically described by the Poisson model. So the P is 1 minus exponential minus and like 2,500 years times t, meaning 1 in 2,500 years times t, which is like 50, or 1 in minus exponential of 50 minus 50 divided by 2,500. You can use this equation to see what is the probability of one occurrence of earthquake if your earthquake is 2,500 year return period and you are considering 50 years. N is annual exceedance probability, which is the inverse of return period. So return period is 2,500 and N is 1 over 2,500. Design life 50 years, so T is 50 years, and so P would be 1 minus exponential minus T 50 year over the return period. Say if it's 457, we can insert it in the equation, and you see that there is 10% chance of happening. So when you design for 475, sometimes casually we call it 500 year earthquake, the probability of at least one time exceedance is 10%. And when we do design for 2475 return period, which we sometimes casually call it 2500 return period, again, we can use that same solution and say that there is 2% chance of at least one exceedance in 50 years. So the two important return periods, and what is the chance of at least one experience during the life. This is 10%, which is high, and this is 2%, which is lower. We normally want the structures to be operable in this earthquake, and we want them to survive this earthquake. Say for this earthquake, after the occurrence of earthquake, we want to be very quick back to normal, and with this earthquake, we want minimum some damages, which doesn't really endanger the life of the people. For earthquake engineers, again, the attenuation relationships are also important. This is a fancy term, but basically what it has is attenuation. What it means is that the earthquake strength reduces with distance. And yeah, so that's what we want. We want to have a relationship that tells us how the earthquake strength or peak horizontal acceleration changes from distance from the epicenter. And that's for different basically moment magnitudes and sitting on the soil or sitting on the rock. Expressions describing ground motion variation with magnitude, source distance, and site condition, accounting for energy loss of seismic waves, and example attenuation of peak ground acceleration. So peak ground acceleration, which is important in earthquake engineering, in structural earthquake engineering, changes with distance, but the magnitude, different magnitude and different focal depths also affect the change of peak ground acceleration distance. But that's all, everything that is to attenuation relationships, and that's what I hear some people who are into geology and earthquake, they like newer attenuation relationships, which keep on changing with better research, but that's all it is to it. The better attenuation relationship give us better estimate of earthquake in our region. Seismic hazard analysis, again, two other terms that we keep on hearing a lot, between deterministic seismic hazard analysis performed by geologists or seismologists and probabilistic seismic hazard analysis. So these two slides give you a quick sense of how they differ from each other in deterministic versus probabilistic. In deterministic seismic hazard analysis, we identify and characterize earthquake sources, so real sources, real faults close to the site of interest. So the site of interest here, and we identify the sources which are close to the site of interest. Some of them are superficial and some are really, they are faults, vertical faults. Then source to site distance parameters. We previously discussed how to estimate the distance to different sources based on the earthquakes that has happened, and selection of the controlling earthquake. So we plot using the attenuation relationships. We plot the ground motion versus distance, and we realize that for our site at the distance of interest, the most important site has been M3 for this case. We find which one is the most important. M3 being this one, source number 3. And then we just use the parameters from the controlling earthquake. So the controlling earthquake is M3, and therefore the seismologists, geologists tell us the parameters of earthquake M3, and we use M3 for our analysis. With probabilistic seismic hazard analysis, the idea is that each one of these sources have a probabilistic importance, like how much is probable that we have an earthquake from source 1, how much is important, how much is probable this year to have an earthquake in source 3, and how much is probable to have an earthquake in source number 2. So identification and characterization of earthquake sources, almost similar with previous one, but the change is that here now we also consider the probability, like throughout centuries, how many times source 1 was active and how many times source 2 was active, and similarly for source 3, and we build up a probability for each one of them. So that's the recurrence relationship, and predictive relationship with uncertainty. Again, like here we just were concerned about the largest response, but here we use basically the probabilistic equation. We combine all 3 sources using the probabilistic relationships. So like say we have 2% of an earthquake with this magnitude and 3% chance of earthquake with this magnitude, and say 4% of earthquake chance of earthquake with this magnitude, and we combine these all 3 sources using the probabilistic relationships. And what we get at the end is, say for amplitude, what is the probability of exceeding certain value? So we have a variation with probability instead of a single value coming from a single source, which was here. Here we had a single value coming from a single source for velocity and acceleration and forces, etc. But here we have a probabilistic value coming out of this analysis. So each one has an advantage and disadvantage and recommended by certain jurisdictions in Canada or US, but always important for us to just know how high level, why they are important and how they are different, so that we are not surprised by seeing the terminology in a quick report. Now moving to seismicity. Again, back to the maps that we were seeing before. Western Canada is the most important location for us, residents of BC. And one of the top sources of earthquake in our region is the Cascadian earthquake zone. We previously discussed that, how the different plates are subducting under each other, and it causes earthquakes. Subduction source caused the great earthquake in 1700 AD, which is the calendar. And so that was 1700, was before people with knowledge of writing live in this area. Therefore, there is no written record of this earthquake, but there are a lot of other evidences that show this great earthquake basically happened. And there are other crustal and subcrustal sources in the region which has caused different earthquakes. 1929, 1970, we will discuss it. So throughout the region, like Mount Baker, which is just south of Vancouver, and these regions are on the island. So this is a good sketch showing the important earthquakes in like recent history, and the great earthquake that happened in 1700. Subduction zone, which goes like what it means is that the crest of this side goes underneath the crust of the continent, and it causes earthquakes. That was the source of the earthquake in 1700. Also, the larger notions show larger earthquakes, obviously. So staying in Western Canada, we talked about the North American plate, and the Pacific plate, and the smaller one, the Foca plate, some other smaller plates that they subduct, they pressure each other and subduct underneath each other, which is the cause of the earthquake. In Victoria region and Vancouver region, subduction of O and the Foca plate underneath North American plate is the potential cause of the great earthquake in future, as it happened in 1700. So there are three expected earthquake types in southern BC: crustal, subcrustal, and subduction. So subduction, we talked about it. Crustal happening through the crust, through the North American plate crust, and subcrustal happens, let's say, going back to this picture, subduction, we know what it is. Crustal happens within the crust, and subcrustal a lot of time happens in this subduction zone, which is already buried, but even inside it, there might be some basically earthquakes happening, and that is called subcrustal. There are three main earthquake zones and areas in BC, in Charlotte region, That's the right streak slip movement, which moves 2 inches per year. And it has caused 7.7 earthquake in 2012. So basically, Queen Charlotte is about this area. There's a fault here, and the biggest earthquake felt recently was in 2012. Subduction zone, when the Fuca plate is subducting under the North American plate, about 1 inch a year, and that was the cause of the 1700 earthquake. Offshore, boundary between Explorer plate and one the Foreca. Again, happens close to Queen Charlotte, over here. So expected earthquakes and their magnitudes. M5 earthquake, which is on the lower side, but it is felt by people and may cause some very, very minor damages once every 5 years. M6 earthquake, which is more important, once every 20 years. And M7 earthquake, which is serious, every 50 years. And subduction earthquake, which is M8, M9, so it's a large value. It happens every 500 years. And last time we said that it happened 1700, so we are getting close to the time when we may have the next one. Next, M8 or M9 earthquake. That's the largest one. But in terms of occurrence, M6 and M7, they happen a lot. And so we should be prepared for those. Some discussion on Eastern Canada. Maybe we can go through this part more quickly so that we get to the end of this slideshow today. So some like Eastern Canada is not really completely without earthquake. As you see in Eastern Quebec, you have some regions, and also in Western Quebec, we have some regions which are really important earthquake zones with earthquakes even greater than M6. Comparison of Western Canada versus Eastern Canada. Return period, earthquakes of like greater than 7 have return periods in Western Canada with half return period comparing with Eastern Canada, meaning that so the vertically greater than 7 happens in other region twice as many as Eastern side, but only twice. So sometimes like we think that there is no earthquake in the east. Seismic wave attenuation due to geologic structure and frequency content. Seismic waves travel much faster in Eastern Canada, so they have less attenuation, means that the earthquake reaches the ground the same as what happened. Fault mechanism in Western North America has extensive surface faulting, so there are some famous faults in California. And however, in Eastern Canada, there is no apparent fault, and everything comes from deep inside. Consequences. Consequences important. Seismic design in Eastern Canada has been of higher interest in recent years. Why? I mean, it's important that seismic design is important in Eastern Canada. Maybe that's not enough because there is not enough. There has not been enough attention to it, and because the construction over there has been old, and there have not been enough attention to earthquake design. So if an earthquake happens there, it's less frequent, but the potential for damage is slightly high because the construction is older over there and with less attention to earthquakes. So earthquake engineering is important in Eastern Canada. Yeah, so back to the 1700 Cascadia earthquake, that's something that we are worried about. Happened in January 1909. The strength or the magnitude was M9, caused by Cascadia subduction. We explained what it is. Known from the oral tradition. So there's an oral tradition. They have told the stories about this earthquake, while there was no written writing tradition. And we know about it because a tsunami, like the earthquake, caused a tsunami that reached as far as Pacific coast of Japan, and Japanese people noted down the date of the tsunami, and they noted down that there were some pieces came in which was not local. And now we know that they came from all the way from coast of Vancouver Island. Those pieces of trees or rubbish, etc. There are also geological records. Like if the geologists look at the layers at the coast of Vancouver Island, they realize that there is a tsunami sand there, which was caused by tsunami, basically. Therefore, we are confident that this great earthquake happened, and we are worried that it may happen again. Okay, I think we can almost stop here because we have only 2 minutes, and that's a good location to stop. The 1700 Cascadia earthquake. Please let me know if you have questions in the next couple of minutes. And other than that, hopefully you guys have a great weekend. Enjoy your weekend, and I will talk to you guys on next Tuesday, basically. I'm waiting here for 1 or 2 more minutes for questions.